So today I will talk about a tunable 2D semiconductor, which is now ready for quantum electronics. And well, just as we are all not traveling much in the last year, I thought I'd bring you some pictures of where I'm actually located at. So here you see two pictures, one from Aachen. So the RWTH Aachen University is one of the biggest technical universities in Germany. We have now more than 45,000 students. And 30 kilometers away from Aachen, there is the research center in Jülich, where with more than 5,000 staff members, we do a lot of technology there. So nice places, and in other times, please visit us. Now, I also would like to start by acknowledging actually the people who did all this work. So what I'm going to show you today actually has been done by the people here shown by the pictures. So I'm just presenting, but the true hard lab work is really done by Luca Panzeres and Samuel Möller in first place. And Luca is actually also available during this talk at Padlet and answering questions, and I'm sure he can do this better than I could do. Now, the topic of today is the use of graphene and 2D materials for quantum electronics. Now, already in early days of graphene research, this material, which in some sense is also topological material, has been identified as very promising for quantum electronics. And there are different ways. So currently we're also learning of bringing graphene together with other materials in some topological phases, and then may use topological states for future quantum computing or similar. But when we talk about quantum electronics, we have in mind to just use other degrees of freedom than just the charge. And I mean, the most obvious one is spin. And indeed, spintronics is an entire field which is based on using the spin degree of freedom as an information carrier. And hexagonal crystals not only allowed to access spin, but they also have this quite unique property of valley degree of freedom. And this we will see leads to the isospin, which also provides a degree of freedom. And I'm pretty sure we will see much more to come where we use valley degrees of freedom as an information carrier. And I will give you a few examples. Now, starting with valleytronics, I mean, you all know the band structure of graphene. You have seen this many, many times. And importantly, there are two different valleys. So there's the K and the K prime valley, and this is all linked with the fact that we have a pseudospin. So when we describe carriers in graphene, they are actually spinors. We describe them by spinor function, by a spinor where the pseudospin actually encodes the superposition of the two sublattice wave functions of the two sublattices A and B, and they give different texture on the two valleys. For example, on the K valley, the pseudospin, which here is depicted by this red arrow, is parallel to the momentum, whereas on the K prime valley, the pseudospin is anti-parallel to the momentum of the carrier. Now talking about electrons here, and actually this then leads to different Barry phases on the two valleys. So we have positive and the negative Barry phase, depending on the valley. And this can also be described by the Barry curvature, which for graphene, which is gapless, is just a delta peak right at the Dirac point, or the point at zero doping. And the Barry curvature has again different sign for the two valleys. And the Barry curvature is one of the, I mean, there's very much physics actually connected to that, because, for example, the valley Hall effect, and we will see later that the Barry curvature also gives rise to topological orbital magnetic moments, which we can actually observe in experiments. Now, the point here is that observing physics based on Barry curvature in graphene is nearly impossible, because we really need to hit the charge neutrality point. The good news is if we are able to open up gaps, then actually the Barry curvature spreads out in K-space, and we get finite contributions also away from the Dirac point. And that's something which will be important. And I think this is also a beauty of this system later. If we can tune gaps, we can also tune the strengths of barrier curvature carriers can see. And this is also one of the reasons here why bilayer graphene is interesting for the Valley Hall effect. So this gives rise to the so-called Valley isospin. I denote it by K and K prime. But if we look now at an electron, we also naturally have the electron spin up and down. So we have these 2 times 2 degrees of freedom, and this will play a major role in my talk. Now let me first talk about spin. Graphene and bilayer graphene has been early identified as a very interesting host material for spintronics and spin qubits, mainly because of the weak spin-orbit coupling, which theoreticians tell us it is around 25 microeV. But also the weak hyperfine interaction makes this group 4 element, mainly consisting of C12 atoms, very, very interesting. I mean, and this is also one of the reasons why theoreticians early dreamed about confining individual carriers and making spin qubits, just starting from work which has been earlier done on gallium arsenide, which really suffer from this problem that there is always nuclear spin in the system. And it's obvious nowadays there are huge efforts on spin qubits in silicon, mainly because silicon-28 is also nuclear spin free. And I mean, you can see just right on top there is carbon. And what I'm going to show today is that we are now coming very, very close to this picture here. So was a tremendous progress in the last 2 years, which is bringing us now quite close to the point where we can really study. Let me already make one promise here. I will show you in this talk at the very end also the measured value of the spin-orbit coupling. So we really have now access to measure such small energy scales. Okay. Now, confining electrons in graphene is a damn difficult task. And this is something I really know from my personal experience. So I started to work in this area more than 10 years ago. And we tried, so when I was still in the lab of Klaus Enslin, and we tried to confine carriers in graphene. And the way we did this is by physically etching graphene to get confinement. And to some extent this worked. So we really could show Coulomb blockade, we could show spin states, but we never could go to the point where we really had a single electron. We never knew exactly how many electrons we have in the system. And one of the really roadblocks in this entire effort was the fact that the edge roughness, when we carve out the structure, is actually too large and gives too much disorder potential that we really get clean confinement of carriers. So the problem in the end is just the band structure. There's no simple way of getting clean confinement. And this is now the point where bilayer graphene enters. And bilayer graphene, it's just 2 sheets of graphene. It's a fantastic textbook example of how one can open up a gap by breaking inversion symmetry. I really like this, and I really hope that this example will enter in many textbooks. So bilayer graphene consists of 2 layers of graphene. So we have in total now 4 atoms in the unit cell, and 2 carbon atoms are placed such that they are on top of each other, where the other 2 atoms are placed such that there is no carbon atom right below or above. And now in this system here, we have now 4 p-set orbitals which matter. We have in total 4 bands, not just 2 as in graphene, and there are 2 low energy bands which touch at the K points. They have a finite mass, and then we have these higher energy bands which are coming from these more strongly coupled orbitals. Now, if we only focus on low energy, we can actually neglect this, and we can really think about this band structure as parabolic bands which touch each other. There's inversion symmetry is still intact, so they touch each other, no gap. The mass is roughly 0.03 of the electron mass. Now, the nice feature of this system is now the fact that these 2 atoms, orbitals, are on different layers. And by applying now an external electric field, I can literally break inversion symmetry by an external knob. And if I do this, then I put these two orbitals on different on-site potentials. And this breaks inversion symmetry and opens up a gap. So it's a fantastic system, and one can do this in the lab. We do this by embedding bilayer graphene in two dielectric layers, and then we have a back gate and a top gate where we can apply now two voltages. So in this case, we put bilayer graphene to ground, and then we have 2 degrees of freedom, top gate voltage, back gate voltage. And now depending on the sign and the strength of this voltage, we can now either open up a gap, as shown here, for example, and keep the Fermi level in the center, or by changing sign, we can actually go to a situation where there's no gap, but we move the Fermi level. So actually, we have two knobs, top gate and back gate voltage, and we can tune the displacement field and the chemical potential or Fermi level, or in other words, also the charge carrier density. So we can actually control with these two knobs, the band gap and the filling, the chemical potential. And well, this is a very intriguing property. And I mean, you may imagine that this is nothing new, what I'm telling you here. And already quite early, people were really looking into this much more deeply. And here you see some early results from 2009, where exactly this idea has been put in practice. And these are very nice infrared microspectroscopy measurements where they really show the opening of this gap. So these are optical experiments, and you see the red data point here. And the important message here is that this gap is roughly 100 millielectron volt per nanometer displacement field. So this is a sizable gap. We can really make use of this. Now, the problem is we need very clean samples in order to use this in transport. Optics is easier than doing transport. Okay, now I show you a typical sample which we use to study the gap opening. So what you can see now here is a backgate structure, which is here. And then we have 4 ohmic contacts to the bilayer graphene, hard to see, because what you mainly see are actually the two HPN flakes, which are encapsulating the bilayer graphene. And then we have some metallic top gate here. And so these are the 2 gates. And then we can measure transport. So this is just a simple 2-terminal measurement. We apply a bias voltage V, and then we measure the current, and then we can actually get the resistance and now study this as function of top gate and back gate voltage. And this is a typical trace or typical map which we get. So now we plot the resistance as function of top gate voltage and back gate voltage. And what you can see, the darker the color, the higher the resistance. So you see, if you start moving out in this direction, it gets darker and darker, meaning the resistance goes up. And so in this direction here, we actually tune the displacement field. We tune the band gap. So the more we go in this direction, the larger the gap. And in this direction here, we tune the carrier density. So these are kind of these 2 knobs we can tune. And now I will show you some cross-section in this plot here at constant displacement field. So now we just take cross-sections here. And so far, all looks fine. But if we now look, for example, at the sample, which we made in early days, so silicon oxide as gate dielectric, then we have highly doped silicon as backgate. We still do all these tricks with HBN bilayer, graphene HBN, and then have a gold top gate. Then actually the resistance trace looks like this. So here should be the band gap. You see here the resistance drops nicely, but the problem is that the resistance is more or less limited to a few hundred kilo ohms. And now we can people were looking into this in more detail, but for example, here you see some data from Amir Siakobi group, on a double-gated suspended bilayer graphene, you see they even have a larger displacement field. So here the expected gap is already close to 100 milli-electron volt. But you still see that the sheet resistance is somehow limited to tens of mega ohms. Now, what's going to happen if we now change just the technology of how we make top and back gate? And if I do this, for example, now with a sample where we evaporate gold onto the stack and then flip the entire stack. So the gold here has really been evaporated onto the HBN, and then we flip everything. We put another gold layer on top. You see that's the same displacement field. We really go now up to the regime, I mean, around 10 gigaohm. And you can nicely see, so this looks now much cleaner. And actually the resistance, so if we go now to larger displacement fields, see that the resistance does not change much anymore. Now we get even better results if we substitute the bottom gold by graphite, then we really go up to values. Now we are above, so somewhere between 10 and 100 gigaohm resistance. So this is really, we are limited now by our setups. So we really pinch off current here. And what you also see is that we have quite steep flanks here, meaning that we have very sharp outlines of our band gap. Now, this is nice. Now, can we extract the band gap from such measurements? And the way how we can do this is now by finite bias spectroscopy. So now we are sitting here at charge neutrality, or inside the gap at the Fermi level, put it to 0. And this would now more or less resemble this situation. So here we have the source and the drain reservoirs. This is our open band gap. We have low bias. Now, if we crank up the bias, at one point we will have transport, because then we can actually have transport through the conduction and valence band. Now, these are measurements we can quite easily do. And typical data look like this. So this is now for fixed displacement fields, and yellow means very low differential conductance. So this is a log scale. So there's nothing flowing in here. You can nicely see such a diamond-like shape. And if we now increase the displacement field, you see that the size of this diamond is increasing. And you see here, this is the bias voltage scale. So this is now millivolt, and this gives us a direct energy scale, because we can now extract the band gap from this measurement. So just taking from this line up to the highest point of this diamond, this gives us the band gap in this material. This is a fantastic method to probe the gap, because if there would be any impurity states, hopping transport, we would not see this, because we have quite a lot of bias which we apply. If there would be something leaking, these diamonds would not appear the way they do. And so now we can extract this energy scale, and what we see is these are now the extracted data, and the dashed line is what we expect from theory. So the conclusion here is we can really nicely open up a gap, and we can use it for transport experiments. Okay, this brings me already to my first take-home message for you. First message, the graphite gating technology makes bilayer graphene a very useful tunable 2D semiconductor. And I mean, we can do, I think, a lot of very nice physics with it. I think the obvious route now would be also to look much more into terahertz physics and devices, because I think a lot of proposals could now work. But I will not do this. I will now show you that we can use now this technology to confine carriers. And therefore, we will now have a look at slightly more advanced devices. So what you see here is, this is now a typical device. So the dashed line tells you where we have the bilayer graphene. There is also, here you see the graphitic gate underneath. And then we have here ohmic contacts to the bilayer graphene. Then we have here a various number of top gates. So we have this finger here, which allows us to completely pinch off current over the entire bilayer graphene flake. But then we have also these so-called split gates. You see there's a channel in between. which allows us actually to open up the gap only below these two regions. Then we force carriers to pass through this channel, and then we have additional gates on top, which allow us now to locally pinch off. And these are kind of the devices we started to play with in 2018, 17, 18. And I think there are now three groups which are kind of following this technology. And I should mention that it really has been first observed and developed in the group of Klaus Ensslin. Now, how are we doing this? So this is kind of the stack. So we have this graphite gate, HBN, bilayer graphene, HBN, and then the two split gates. And if we tune now the voltage on these two split gates and the graphite gates, such that we completely deplete the electrons from these outer areas, then we have a one-dimensional channel. And now having this one-dimensional channel, we can now make use of an additional gate layer. So there is another alumina layer now separating this green gate from the yellow one. And now we can apply potentials here and simply interrupt this 1D channel in such a way that we get a small charge island, which is separated by this, for example, p-doped region. And we use the band gap, which we also have in this region because of the displacement field originating from the graphite gate. We can actually separate this whole electron island from the whole leads. And this way we can make quantum dots. And here you see a typical device. So we have several of these finger gates, and now we can use just one to make this quantum dot. And typical measurements now look as following. So here we start. So this is now conductance as a function of gate voltage on one of these fingers. And in this region here, we still have transport. So we have a p-type channel. And we start to increase the voltage here, meaning that we start pushing down the band edges to lower energies. So here we are still in this regime where everything is p, so whole transport. And if I go now far enough down, we make this quantum dot here. So this is now an electron quantum dot. And you see that there are Coulomb resonances appearing. And you also see that they are actually grouped in packets of 4. So there's no electron sitting here, then 1 enters, 2, 3, and then the 4th one. And then we have another 5, 6, 7, 8. And you see that the spacing here is large. And then you also see a 12 spacing is large. And this is something we can understand very well, because what we do here is we have an artificial atom now in this bilayer graphene system. And we know that we have a 4-fold degeneracy. We have the electron spin up and down, and we have the valleys. So we need to first fill up the first shell. This is this packet here, and then we can fill up the second shell, and then the third one, and so on. So now we are at the level, we know how many carriers we have. Okay, and just for people who are not so much familiar with quantum dot physics, let me go a little bit slower. So what this really means, this trace here, is that if we are, for example, sitting here in this regime, there's no current flowing. And the reason why there's no current flowing is because now we have 2 electrons in the system, and we don't have enough energy here from on our source to jump up to the 3rd one. So this is, and the second one is already blocked, so there's no transport happening. And the spacing between these energies here is actually a Coulomb charging energy plus the quantum mechanical level spacing. So both matters here. Okay, so also Coulomb energy, charging energy is important. And now if I, with my gate voltage, I can actually now change the energy in my dot states. And if I do this, then I go, for example, to this situation. So this is now tuned in such a way that I can now really hop onto this level and hop off again, and then I have transport. And this gives rise to this peak. So this is the way how we should really think about this system. And now we can actually look what happens if we bring such a system into a magnetic field, because then we can now really identify which kind of states do we have in the system. And if I show now such, or if we do such experiments, so this is now an out-of-plane magnetic field. So the magnetic field is pointing out of the plane of the bilayer graphene, and the yellow now means these are the Coulomb resonances. So this is now the first Coulomb resonance for the transition from 0 electron to 1. And then we have here the second, third, and then the fourth. And then you see the large spacing here. And then again, 4 lines, large spacing here. And you can already see here that there's a lot of stuff going on. For example, we see that for the first transition, this line runs down in energy. And actually, so does this one from 4 to 5 runs down, and also from 8 to 9 also runs down. And we can actually follow these lines now. And so this looks like this. So here we have now that I just marked this. The important point is that we can now, from such a plot, and the fact that we do have level or potential level crossings. So for example, if I look at this feature here, we see that there's a line running down and then gets continued here. So it really looks like an avoided crossing, but it's not an avoided crossing here. The point is that we still need to pay the charging energy because we add one more electron. So what we can do from such level crossings, we can actually subtract this energy. We simply shift these lines together. And this way we can actually extract information on level spacing. And this is how it looks like. So this is now, I just convert now my voltage scale into an energy scale. We can do this from bias measurements, which I don't show now, but this is now all at 0 Tesla. And what you can see again is that the large spacing is at going from the 4th to the 5th electron and from the 8th to the 9th. And this is the addition energy. Addition energy means both charging energy plus level spacing. But now if we go to these points where we have the level crossings, we can actually extract the charging energies, because on these points we only have charging energies. Once we have the charging energy, we can also extract now the level spacing. That's just the difference between the red curve and the green one. And now you can very nicely see that the level spacing between the first shell and the second shell is almost 2 milli-electron volt. And you see that this is also consistent for the next shell, where we go then from shell 2 to shell 3. So we really understand the systems, and the energies are quite reasonably well agreeing to what we also expect from geometry. Okay, so what now about the valley? So now I showed you that we really understand this filling sequence, but what can we now tell about the valley degree of freedom and the spin degree of freedom? And now I need to tell you a little bit more about the Barry curvature and the connection to magnetic moments. So now let's focus on electrons in bilayer graphene. So this is the simplified parabolic band structure. So we look at the electron side, and now in this system, because it's gapped, the Barry curvature has a finite extent in K space. And for K prime, the Barry curvature is positive. For K, the Barry curvature is negative, as I introduced at the very, very beginning. And actually the Barry curvature, I mean, this gives rise to an anomalous velocity term. I mean, people which are aware of the Valley Hall effect know this, but it also leads to a topological orbital magnetic moment. So we really can think about having a positive orbital magnetic moment for K prime and the negative magnetic moment for K. And this will become important because these orbital magnetic moments, they interact with magnetic fields. And this is also what we now call the isospin property. Okay, so now let's just different colors, but same physics. So this is the Barry curvature, and this is now for electrons. We have positive Barry curvature for K prime, negative for K. And now we just look at the electrons, and now we can actually sketch what we expect. So what we actually expect is having negative orbital magnetic moment for K, positive for K prime. And that means if we now look at an energy scale, we will see if the K prime states, they will move down in energy because the magnetic moment is pointing upwards in P set, and the K states will move up in energy. Now, you could say, well, what about spin? And okay, before I include the next picture, I need to tell you that the typical G factors, so this is, we can describe this linear dependence also by a valley G factor, is roughly an order of magnitude larger than the spin G factor, which is 2 in carbon. So actually the picture which we expect looks like this. So we have 2 lines running down, so the K prime spin up and K prime spin down, and analog, we have the K spin up and K spin down moving upwards. And this, the difference here in the slopes will be governed by the G factor 2. And the story is not yet at end because I told you at the beginning, we also have spin-orbit interaction. It is small, but it's there. And if we now include spin-orbit interaction, this will actually lift the energy of the Kramers doublets, where spin and isospin are pointing in the same direction. They're energetically different than the situation where they point in the opposite direction. This is just the Kane-Millet type spin-orbit interaction. And if we now include this, then our picture looks like this. And people which are familiar with nanotube physics, I mean, they may have seen such similar schemes already. Now, what does the experiment tell us? Now, if I go back to this data and I now extract the peak positions, I simply shift them together to the point where they touch. Then I get a picture which looks like this. So this here is now energy axis. Here is the out of plane magnetic field. The color just encodes the intensity of current. And what you can very nicely see here is that we have states moving down quite steeply here. These are K prime spin up states. Then we have K spin down states, which both start here and move up. And then I can follow this by the K prime spin down and the K spin up. So here we really have these 2 Kramers doublets, and then we have the slopes, and actually we can fit all this here with just 2 slopes. So spin G factor of 2 and valley G factor of 30, and it really kind of matches this picture I just showed here. Now, there's one very interesting aspect. It really looks trivial and very similar to nanotube physics, but it is different. The point is the nature of this valley-dependent topological orbital magnetic moment. It really depends on curvature, barrier curvature. It depends on the gap size. It depends on the size of the wave function. How much does my wave function see of this barrier curvature? For example, if we go already to the next shell, okay, this is just the filling. If we go to the next shell, we see that here already the magnetic moment is different because the wave functions will be different. And so this looks slightly different. Now, one important remark here, what we see here, this gap here is not yet the right gap of the spin-orbit coupling, because here we also have Coulomb-Coulomb interaction included, because we do this measurement by filling up electrons. And so we also need to be careful here. But I will show you we can do these experiments much more careful with just 1 electron, and then we don't have interaction. And then we can really map this out. This will be at the very end of my talk. Now, let me first, before going into this, I will show you what's going to happen with holes, because now I talked about electrons. So what about holes? And can we cross over from holes to electrons in just 1 device? And well, I would not pose this question if the answer would not be yes. And what I show you now is just to give you also a flavor of how more advanced the devices nowadays are. So this is kind of one of our later generation device. Now here we already have 3 metal layers on top of the bilayer graphene. So we have these split gates here, which are on this layer. And then we have 1 layer of alumina. Then we have 1 set of finger gates on one And on top of that, we have another layer of finger gates. So they are kind of interdigitated. And this gives us much more tunability in this system. And what I show you now is a situation where we again start out by having this 1D channel tuned such that we have hole-like transport through the entire device. And so this here is now a map of this left and right barrier gate for a fixed plunger gate voltage. So the central gate here is fixed. And in this corner here, so this is labeled by 1, here we have hole transport. And if I now move in this regime here, 2, you see that we have these resonances here, which have this curvature here. This, we actually start forming a hole dot because we start putting larger potentials on the left and right barrier gates, and then the bent edges actually move down. We get this hole dot. And actually, this is also well reflected in this curvature, because if I put now more voltage on the right gate here, then I start to couple it more strongly to the left gate. So I shift the dot to the other gate. This explains this curvature here. And if I go now in this regime here, we have a double quantum dot made of electrons. And what I'm going to show you now is a very similar measurement, but with a different plunger gate voltage. And just to help you, we put now a mark here. So this is, we keep the position, this cross will be the same, at the same voltages, barrier gate left and right in the next plot. Now, if I go now to higher voltage in plunger gate, I simply shift the entire plot upwards. So again, here in this regime 1, we again have hole transport. But if I now move in this regime here, you see now the curvature, the sign of the curvature changed. And here we are now in a regime where we simply have one big electron quantum dot. And you see also the reason why the curvature changes, because if I now put a larger voltage, for example, on the left gate, then I pull this further down and the center of the dot moves towards this left gate. And so it couples more strongly, which explains this slope. And you see again, here is this cross, which I showed you before. I mean, here this cross was in the hole dot regime, and now it's in the electron dot regime. So what I will show you next is simply we keep now the barrier gates fixed, and we just play with the plunger gate. And that's what we see. So this here is now the trace. So this is a log scale of conductance. So here you see hole dot states. So this is the last hole, and then we empty, and then we have a gap. Then we have the first electron, second electron, and so on. So we really tune with a single gate from this hole quantum dot to the electron quantum dot. And now I show you also some bias spectroscopy measurements, and they look as following. So here you see now the diamonds, fourth hole, second hole, first hole, and then the gap. And this gap really matches the 20 milli-electron volt, which we know from the band gap adjusted by the split gates and the back gate. And then we have here first hole, first electron, second electron, fourth electron. So we can really tune this system to go from holes to electrons and control the number. Okay. Now, we can also now check how the orbital magnetic moment texture looks like for hole states. So this part, this picture I've shown already. So this is now electrons and holes. And you see that for holes, actually, they get reversed. So now for holes, our K states have a positive orbital magnetic moment. Now this picture I already have shown you. And now I'm adding holes. And you see, I mean, the energy of holes would actually point downwards. But now actually the fact that the role of K and K prime switches, this is not a perfect mirror image, but it really looks just the same. Okay, so for electrons, the K prime states are moving to low energies. For holes, the K states move to low energies. Okay, and here the K prime states move to high energies. Okay, now let's see what do we see in experiment. So this is how a calculation looks like as function of out-of-plane magnetic field. You see the K prime states move down, K states move up, so just different colors, but same physics. Now, if we use this data and add charging energy, then we get something like this. So you see now each line here is appearing in pairs because of spin, which we cannot resolve in this experiment. But you see that the electron states should move downwards in energy and they should move upwards. Okay, to make it short, this is what we see in experiment. You can see that there is a tendency of the hole states to move upwards and for the electron states to move downwards. And if I make an average of this, it actually looks like this. So you can see, and this is what we expect from theory, are the colored line, and the data points are coming from this experiment. So we really can, for now, a finite magnetic field, kind of polarize the valley differently for electrons and holes. So we quite well understand this system. Now, let me, at the end now, very briefly talk about the spin-orbit coupling energy. And so this is the spectra I already showed you. So this is really kind of the single particle spectra or single electron spectra of bilayer graphene quantum dot. And we expect this energy scale somewhere in the regime of a few tenths of micro EV. So it's quite challenging to measure. And I can just, if you're interested to learn more, there are two very recent preprints on arXiv which really show this spectra. And so the way how we were looking into this is we were looking into a double quantum dot system where we can have much higher energy resolution. And actually the energy resolution is high enough to also make a statement on the KK prime valley mixing. And this is now kind of a disorder-induced mixing of the valleys. And I can tell you this energy scale, well, we cannot resolve it, but I show data. So the device we are now studying is a double quantum dot, again, with this technology where we have interdigitated finger gates. We can make now two dots, source, drain, lead, and we can bring the system in to the state where we have no electrons in both dots. And we simply now study the transition. So the very first triple point pair where we only transit one electron. So one electron hops from left to right and then leaves the system. And this way we can actually do spectroscopy of the single state spectra. And what we are looking at now, so this is now at 0 Tesla, exactly this triple point where we have just one single electron in the system. And what you can see here already at 0 Tesla, if I make a line cut along this detuning axis here, this is now an energy axis, you see that there are actually two states. So the first one is easy to understand. This is simply the ground state transition from this Kramer's pair to the very same in the right dot. But you see that there's another feature, this feature here, and this is actually the first excited state. And this is actually, so the hopping through the other, so we are spin conserving when we go through a dot, but we can access different values. And this gives actually a rise now to this second peak where we really now tunnel through the upper Kramer's doublet in the second dot. And this energy scale is exactly the spin orbit coupling. Now we can prove this when we now do this as function of magnetic field. We see that these lines shift, and there's also an additional line, this yellow line appearing. And we can understand this very well because if we now make two of these copies of this spectra and now look at these transitions, for example, this transition 2 here is shown here. So this is moving up in energy, and then we have a transition which actually will first move down and then vanish, and then we have another transition which then appears and moves up. Well, I make this story here short. We can understand all these transitions, and if we look now at such a map, so this is now measured along such a detuning axis as function of out-of-plane magnetic field. You can very nicely see that at 0 magnetic field, we have these two states. And then we have this transition, which actually moves down. And then we have transition 4, which appears moving up. And this distance here gives us the spin orbit coupling. And the distance between these two transitions is just twice the spin orbit coupling. And well, you can already see that if we would have now a KK prime mixing, then we would get an anti-crossing here at 0. So just from this, we can get an upper limit of what we can currently say about the KK prime mixing. And I think the important numbers here is that the spin-orbit coupling strength, which we extract from this experiment, is 65 microeV. This is also well agreeing what been observed in the group by Klaus Enslin, where they have 80 microeV, and we can say that the KK prime scattering, so the disorder-induced mixing, is smaller than 20 microeV. And this is, bringing me to my second take-home message. I think we can say now that there's a full understanding of the rich single particle spectrum of bilayer graphene quantum dots, and I really want to point out that this is a rich spectrum in the sense that this topological orbital magnetic moment really depends on the band gap and also on the wave function of our dot states. Now, I could easily talk for one more hour. I mean, you can easily imagine that we can now also very well tune double quantum dots. We also have first results on dispersive readout, and we are currently working on getting faster readout and to really get all this technology machinery working, which is necessary for implementing spin qubits and valley qubits. We also have already first data on relaxation rates. So this is just a first limit, mainly limited by the way how we measure. But I mean, everything looks fine so far. And I think we are now on a way where we can study much, much more. And so third message, bilayer graphene is a fantastic platform for quantum electronics. And this is my summary. So I think I showed you that by very clean bilayer graphene heterostructures, we can have a well-defined gap. We have now control on confinement. We know how many carriers we have. We can tune controllably from holes to electrons and back. Spin-orbit coupling is understood. We also learn more about the valid degree of freedom. We are currently studying 2 electron spectra, very complicated, but very interesting. And if you're interested to learn more, well, there is more literature on this. You see Luca Banceros is really pushing this very hard. And well, if you're interested to learn more about this subject, so today I didn't present any equations. So if you would like to see more equations, I also would like to highlight that I will be teaching a class on physics of graphene and 2D materials on Zoom starting in April, mid of April, where I really promise to really go into much more details and back this all up with simple concepts. So just drop me a line if you're interested. And with this, I would like to stop. And thank you very much for your attention.